So chapter 8 really isn't terribly new. We're going to be doing hypothesis testing, but it's kind of a different way of answering the same question that we did in the previous one. So let's start with the idea that you have a coin, you assume it's fair, you flip it 100 times. Would you think if you got 53 heads, you'd look out of the 100, you go, wow, that's really, it's not a fair coin, right? Right? Well, would 53, or what would we expect, right? What would we expect if it was a fair coin, right? Then the probability should equal 0.5. What did we actually get? Well, we got, this is from our sample, right? We got 53 out of 100, so we got 0.53. Would you expect that to be unlikely or likely to happen? Well, if it's 50% is what we're expecting and we got 53%, that's pretty close. And so I go, yeah, that coin, you're going to have some variation in sampling, not freaking out about this. What if we got 85 heads? Well, we would have 85 out of 100. That's a little further away than 0.5, right? So we go this and we go, man, maybe this is significantly far away from what we expected, right? So at what point do we say, yeah, this is now significantly far away? Because we thought, well, 0.53 wasn't that bad. What about 0.55? 0.6? 0.65, 0.7. Now I start having people going, that's where you start looking at your coin going, yeah, I don't know about this coin. How am I getting 70 out of 100? At what point do we get far enough away from what we expect for it to be significant? That's the idea of hypothesis testing. And the good news is we have a way of handling it mathematically. And we will also be using the PRTC. A lot of these are going to be the same. So we're going to start by P. State the parameter. R. And this will either be P equals for proportions, true, proportion, or mu equals, true, mean, whatever. They also have tests on standard deviation, but I won't be focusing on those. The requirements are basically the same as chapter 7. So once I've defined whether I'm doing a proportion or a mean, if it's a proportion, check the requirements for portions. If it's a mean, check the requirements for means. It's the same as before. SRS. How about an SRS there? And then here we get normality with at least 5 successes and failures. And then the independence, I'm actually not as concerned about that. The independence and the probability staying the same. That's if you were actually running this, you would just want to verify that. But these are the two I'm wanting you to focus on the most for the test. For means, well, SRS. How do we get normality? Right? Well, we'll get normality, either it'll be given, or the sample size greater than 30, then the central limit theorem comes in, or you check it. We said with the box and whisker plot or a normal probability plot are kind of my two go-tos on that. The T is going to be a little different. We are either going to have a 1 prop Z test, okay, that will be for proportions, or we will have a 1 sample T test, and that will be for means. So kind of think of this still as being separated, okay? So proportions, means. Okay. You can also have a 1 sample Z test for means, But remember, that's only if sigma is known. But this, when you run the test, there's actually a couple more things to this. So you have to make sure, and this is actually where the homework is going to start. I really like how they start by focusing on just the hypothesis tests. You have to list what are called our null and alternative hypothesis. Okay? Our null hypothesis, this is a little 0, so H naught. Okay? Basically says we assume nothing. We assume that the claim is true. So the example that we were looking here with proportions, we'd say P equals the claim 0.5, but it'll be P equal to some claim or expected amount. Alternatively, if I'm trying to prove that the coin is not fair, I would do maybe not equal to the claim. If I want to prove that it's biased a certain way, I could do a greater than, or I could do a less than. Same thing when I'm doing with means, but our null and alternative hypothesis, instead of being about proportions, will be about mu. Mu is equal to some claim. Mu is either not equal to, greater than, or less than. So it's going to be one of these three. The other thing we emphasize on here is that you have to put the test statistic. So for this one, it'll be either Z or T. You have to include the p-value. And for T specifically, you have to include degrees of freedom for the T. Okay, so that would be specifically for the T test here, you would do degrees of freedom. Okay, and then based on that, we're going to write a conclusion. I'm going to go ahead and save that for the end, just when we get a little further. But so far, it's going to be focusing on just this new part, this null and alternative hypothesis. And if we can get our brain around that, then the rest of it's going to be very easy. Just going to be a matter of following down a list of steps. If people make mistakes on these, what it tends to be is, first of all, you got to state the parameter, checking the correct requirements. Once you have that, you should run the right test. But if somebody runs the wrong test, it's probably because they didn't state the parameter and identify that correctly at the very beginning. Getting these test statistics, that's going to be given to you by the calculator. Knowing the null and alternative hypothesis is probably one of the most complicated things we're going to do, and that's what we're going to emphasize on at the beginning. And then writing the conclusion, that's actually pretty easy. There's going to be two generic conclusions I'm going to want you to use. Okay? So a light bulb manufacturer claims the mean life is more than 750 hours. So what they're going to want you to do is they're going to want you to set up just a null and alternative hypothesis. First of all, am I going to be dealing with a mu or a p? Am I dealing with a mean or a proportion? There's a hint right here when they said mean life. So since we're dealing with the mean life of the battery, we would use mu. That will go for both of them. You have to include that parameter symbol. The null hypothesis, right, we call this H naught, or the null hypothesis, basically means we assume not. We assume nothing. Null also means to cancel or to have nothing. If you have a contract and it's null and void, basically it's empty. It's worthless. Okay. We assume nothing. To have not, the word not here is kind of an old English word, but to have not means to have nothing. Okay, you would have seen that more in Shakespearean. They would use not. Okay, so we assume nothing in the null hypothesis. It will always be equal. We assume that the claim is true. We assume not. Okay, so the claim in the situation is 750 hours. the null hypothesis will always be equal to. Alternatively, this is where we have to decide. Well, if they use the word greater than or less than, I'll use greater than or less than. If they just say different, then I'll put a not equal to. Here they say they think they're claiming it is more than 750. So more than means we're going to try to prove greater than 750. And that's how we would set up the hypotheses. The other thing they'll have you do is they'll have you identify which of these is the claim. So the claim is that it was more than 750. So right here, this would be the claim. A research organization reports no more than 33% of the residents in Ann Arbor, Michigan are college students. Okay, so let's start with, is it going to be mu? Somebody stop me, right? No, they said what? 33%. So since we're dealing with a percentage, they don't say average in here, we would put P is equal to, what's the claim? Okay, so that claimed number goes right there. Now, they're reporting that not more than 33%. So not more than would mean what? Well, right, 40 would not be not more than. So you have to basically say, well, this means less than. If you're not more than, that means you are less than. And that's a little confusing, but be careful. Which of these is the claim? This is what we would be testing to try to prove. The claim won't always just be the hypothesis, or the alternative hypothesis. Okay, so I guess we said H naught. I should identify this. I'll be calling this the alternative hypothesis. Hence the A. HO and HA. Some books will use H0 and H1. I don't like that as much. I like the A for the alternative and the O for not or null. Other people will call these ho and ha. I won't. So just kind of, if you want to do that, that doesn't hurt my feelings, but that's not really proper. The results of a research study show the proportion of people in Western U.S. who use seatbelts is 84%. We have a percent, right? So just setting up the hypotheses. We're dealing with a P. The claim number is 84%. Did they want us to prove greater than, less than? No, they made a claim that it is, that it equals. So this is the claim this time. They're saying it is 84%. So the alternative to that, if they're claiming that it is 84%, we could do less than, we could do greater than, but if they don't use those words, this is where we would do a not equal to. We're basically just trying to prove that it's different than 84%. That could be greater than, that could be less than, either or. Study claims the mean survival time for certain cancer patients treated immediately with chemotherapy and radiation is less than 24 months. That's kind of depressing. What are we dealing with? Mean survival. So that would be mu. The null hypothesis, I know I see a less than, don't put a less than here. The null hypothesis is always what? Always equal to. We assume not. We assume nothing. We just assume, okay, let's say it's 24 months. Alternatively, they're claiming it's less than 24 months. And that would be the claim. Okay? So the way that we run a null hypothesis is basically we assume that this null hypothesis is true. We assume that it's true, and then we test that if our statistic we got showed up, what's the probability of it occurring? Okay? So in all of these, basically what we're doing is we're taking whatever the H naught is, okay, and we're taking what either P equals, and we're making that, we're assuming it is the truth. or we're taking the null hypothesis and we're taking whatever the mean is that they say, and we're taking that as the truth. And then what we do is we find the probability of either I get some p hat that's different or some x bar that's different, and I go, what is the probability of this occurring if the claim they made was the truth? If the number they claimed about was the truth. Okay? So these are instructions for your TI 384. We will be using menu, statistics, tests, one prop z test. Okay? So from running this test, like I said, we are going to get a, well, we're dealing with proportions here. So I'm going to have a null hypothesis and alternative. Let's go ahead and just do the t. This will be a one prop z test. So you're going to run the test. It's going to give you a z-score. That's called the test statistic. You have to report that. It's going to give us a p-value. And we will have an alpha level. The alpha is called the significance level. And it will either be 5% or something given that they ask us to test against. Okay? This is basically what we are considering as the allowed probability that if I'm going to allow there to be a 5% probability, and if that occurs, I'm going to say, well, it could have happened by chance. Okay? The p-value is the actual probability of our statistic occurring by chance. Okay, so we're going to calculate, it'll give me the probability, and the significance level is basically anything, if it's above that, we say it's not significant enough. Anything less than that, we go, well, it's unlikely, and we will reject it. Okay, so the way we do this now, so you're going to list all this, don't forget part of the test will be the null and alternative hypothesis. So p is equal to, p is either not equal to, less than, or greater than. Okay? They have some phrases down here. I'm going to give you the exact phrases I want you to use. What you'll do is you'll say, look, if, or you'll say, well, since. So one of two things is going to happen. Either alpha is, phrase it differently. Either the p-value is less than alpha, or the p-value is greater than alpha. If it's less than alpha, what we do is we call that significant. Our probability is less than that 5%. We go, this is not likely to occur by chance. Basically, our results are unlikely, which means the claim that they made is not true. If this occurs, this is called significant. We say, since the p-value is less than alpha, we reject the null hypothesis. I'm going to want that in words, and conclude the alternative. This is called significant. So the results are significant. If the p-value is greater than alpha, then we said, I'm going to allow a 5% chance. We got 6%, 7%. We go, you know what? That could have just occurred by chance. So what we would do is we would say, since the p-value is greater than alpha, we fail to reject H naught, put that in words, and we're done. If you cannot reject the null hypothesis, you don't get to really conclude anything. We've not proved anything. We just can't disprove the null hypothesis. If you want to add something here, you could basically say the results are not significant. Okay, but we don't conclude anything when we fail to reject. Just basically our results were not significant enough to reject. Okay? I know this seems a bit overwhelming. What we're going to do is we're going to go through it. A lot of it's new. A lot of it's not new. A lot of it's the same what we've seen as far as, doing the PRTC. The difference is the checking the test, how it runs a little differently, and the conclusion. But the first assignment is just going to focus on just the hypothesis, which really will help kind of settle that out. So a medical researcher estimates no more than 55%, there's that stupid phrase again, of U.S. adults eat breakfast every day. This is a claim. Okay? In a random sample of 250 U.S. adults, that's a sample size, just like it was, 56.4% say they eat breakfast every day. This right here is not a claim. This is actually from a sample, right? So this is a sample proportion. This is a p-hat. Is this enough evidence to reject the researcher's claim? PRTC. First, what are we dealing with? Well, this is a proportion, isn't it? So P is equal to, what are we doing? The true proportion of U.S. adults who eat breakfast every day. Okay? The requirements, not new. Data must be collected what? What did it say? Estimates, blah, 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 NA. So this I'm not going to put assumed. They've told this to me, so it will be given. What's the other requirement? I need successes and I need failures. They didn't give me successes and failures. They gave me a percentage, right? I need at least 5 successes and 5 failures. If they don't give me that amount, what I do is I take the successes would be n times p hat. That's n times p hat. 250 times 0.564. We're looking at 141 people there, right? And that is greater than 5. I would argue that. Okay? How many failures? That must also be greater than 5. I can do 250 times the other 0.436. Or I can say, well, if there are 141 successes, there must be 109 failures, which is also greater than 5. So those are the requirements. Now we run the actual test. How do I run it? Well, I will use a 1 proportion z test. It's very tempting to sit here and just run the test in the calculator. I can go here and go menu, statistics, tests, or was it 1 proportion? But right off the bat, it's going to ask me about the hypotheses. So this should stop you. Before you run the test, you should stop and think about what the hypotheses are, okay? So when you get to that point, go, oh yeah, I need to list the hypotheses. I've had some teachers I know that will say PRTHC to remember that the hypotheses go here with the test. I don't really care, just make sure that you have the hypotheses. Okay? Since we're dealing with a proportion, I'm going to put P equals, what was the claim? Well, they said 55%. Right? Alternatively, is there enough evidence to reject the claim that it is not more? Not more means what? Less than. And that makes this the claim. Okay? So in this situation, now we're ready to run the test. Actually, I'm going to change this. This is what I would have done on this one. And I would run the test, but actually, this is going to be a greater than, and I don't like the wording on this, but the goal here is to reject this claim. So this, what we're trying to do is prove the claim. That's not really going to be what we want. This is going to be a greater than. Because if I can prove greater than, I can reject the claim of less than. I will do my best not to word things like that in the quizzes and the tests. If you feel like something is worded like this confusing-wise on the quiz and test, talk to me. I can be convinced. I would argue if you ran this with less than, that makes sense based on no more than. Anyway, they want us to reject it, so we're going to do greater than. So sorry about that. This we can do, right? Very frustrating, I know. Okay. So where were we? Running the test. Menu, statistics. We're doing a test, not a confidence interval. So test, and specifically it was a one proportion z-test. P naught is basically the claim. What was the claim? They said 55%. That's right here. What I need to do now is I have to put in the successes. Well, they didn't give that to us, but it's a good thing we calculated it, so that's going to be helpful. What was it, 141 out of 250. So you're going to use those numbers. So this isn't just a bunch of busy work. Those are numbers we're actually going to use, really just the 141. We need that number of successes out of 250. And then last but not least, just make sure that you choose an alternative that is what? You said greater than. Okay? So what do I need to write down? If you're not sure, write everything down. But what I need to write down is the test statistic and the p-value. So 0.445 and the p-value of 0.328. And then how do I write this conclusion? I've given you two phrases. Oh, I need an alpha, right? Did they give me an alpha? Did they say at this significance level? No? So if they don't give me an alpha, we use 5%. So what is our conclusion? Since p-value is compared what? Well, it's greater than alpha, isn't it? So I don't have to make all this up. What I would do is I would just go to my notes and put this on a note card and say p-value is greater, we fail to reject, results are not significant. Right? Since this, we fail to reject that P is equal to 0.55. Notice I put that in words. Okay? You're not going to just write H naught there if you want full credit. And conclude the nothing. So leave that alone. See, I was going to fall for it, right? Don't do it. If you want to write something else here, write the results were not significant. We could not disprove the claim. Okay? So that's going to basically be it for running the test. I know that seems like there's a lot, but keep in mind, each of these is going to be worth like 5 points. Okay? So I'm going to give you a point for stating the parameter. Do that. You got a point. I'm going to give you a point for checking the requirements. Do that. I'm going to give you a couple points for the test. You're going to choose the right test, right hypotheses, and then I'm going to give you a point here for the z-score, p-value, alpha. So there's a lot of points right there. But you're like, well, what if I messed up on my hypothesis? Well, that's like 1 point out of 5. That's going to change your z-score, your p-value. It's going to change a lot of things, but that's okay. I can keep track of that. If that's the only mistake you make, you still can get 4 points out of 5. Don't like mess up on the requirements, then run the wrong test, then state the wrong conclusion, then you're throwing away all your points. But if you can state the parameter, check the requirements, run the right test, state the right hypotheses, test statistics, and conclusion, I'm looking at 5 total points. Okay? So little mistakes aren't going to be right or wrong. I will be grading these by hand. Okay? I do want to discuss real quick what the heck we just did. Okay? But this is basically the extent of what you need to do, but I want to just take a second and go, why or what the heck did we just do? Okay? Well, we got a z-score. How did we get that z-score? Well, we assume that h0 was the truth. Okay? So prior we've had a formula for z of the statistic minus the parameter divided by the standard deviation. Okay? Well, if we assume this 0.55 is the truth, then basically that 0.55 goes right here as the truth. What's the p-hat? Well, that's the actual result that we got. That's that 0.564. So you can actually fill in all these pieces and we could get the z-score. Okay? So I want to do that just to show you. I'm not going to expect you to do this on the test. Okay? But I can start with 0.564 minus the truth claim divided by, this gets a little sketchy, the square root of 0.55, 0.45 over n was what, 250? This should give me a z-score of 0.444949. Isn't that the same as what they got? Right? .4449. Alright, so that's why we did 0.445. Okay? So what did they do with this then? Well, we wanted to find the probability of this occurring by chance. Since this was a greater than, okay, since our alternative was greater than, we call this a right tail test. We find the probability of us getting, if 0.55 is the truth, we find the probability of getting our 0.564 or greater. Basically, I already have this as a z-score. That was as a z-score 0.445. So I would do norm CDF to the right of this 0.564. So that would be a z-score of 0.445 to infinity with a mean of 0, standard deviation of 1. We're finding the probability of this right tail of getting greater than that claim. Okay? So that would be, where is it? Norm CDF. Our lower bound was that decimal, 0.4449, just to keep a couple more decimal places. Upper bound, a bunch of 9s, 0, 1, 0.328, some round off error, right? 0.3282, 0.3282. So we did pretty good on that. And that is basically our p-value, 328. That's a lot that the calculator is doing for us, and so appreciate that. But I want you to understand that this is basically the probability of us getting our result, right? And what we do is we test it against an alpha of 5%. We say if you're anywhere past this, if you're anything to the right of this 0.05, that is considered significant. We didn't get that far. We had too high of a probability. We're like, yeah, it could have just occurred by chance. Anything to the left of that we call not significant. And so that 0.05, 5% was much further to the right, okay? And we got a score that was not that far away. So it was not significantly far enough away, okay? I am going to keep doing this because I want to make sure we understand how the tells go, but focus on, for the test, know how to run PRTC. Environmentalist claims no more, that more than, that's annoying, all right. 58%, that's the claim. British consumers want supermarkets to stop selling GMOs, basically, genetically modified food. You want to test this claim. You find a random sample of 100 British, sample size, 67%, that's from the sample, that's not the claim, that's the P-hat. Okay? PRTC. What is our parameter? True proportion of Brits who I'll just get all wordy with it, want supermarkets to stop selling genetically modified food. Okay? Get wordy here. It's going to save you a lot of effort later on. Don't throw away an easy point right here. What are the requirements for a proportion? Data must be collected randomly. You found a random sample, so it was stated. We need at least 5 successes. They didn't tell us how many successes. So how many successes do we have? Well, 67% of the 100. That's 67. That is definitely more than 5. How many failures did we have? That would be the remaining 33, which is greater than 5. You could have also done 0.33 times 100. Okay? So we have our successes, we have our failures. We'll use this in a minute, but that basically meets the requirement. I've got 2 points so far. Let's run the test. We're going to do a 1 proportion Z test. I would like a 3rd point, and so I'm going to go ahead and set up our hypotheses. Null hypothesis, using the P, always equal to, what's the claim? They claimed 58%. Alternatively, they claimed that more than 58%. What are we trying to test? You want to test this claim. So we want to test more than 58%. We're not trying to disprove the claim. So at least this one's not crazy. I'm not going to get angry. This one is, we're just going to do more than 58. I'm trying to prove this claim. Okay? I think we're ready to run this test. The actual running of the test is pretty easy. Stats, tests, 1 sample, or 1 prop Z test. What was our claim? 58%. How many successes did we see? 67 out of 100. And we're trying to prove greater than. Z-score is 1.82. P-value, how about 0.034? Alpha level. Did they give me a significance level? They didn't, so we're going to use 5%. Based on this, conclude that since the p-value is, how does it compare to alpha? Well, it's less than alpha. So I go to my notes. Less than is significant. That means we get to reject the null hypothesis. Reject that the proportion is equal to 0.58. And conclude the alternative, that it is greater than 0.58. Yay! This is significant. This is what we're looking for in statistics. We want to test and we want to prove and disprove things. It's not valuable, not completely invaluable, but it's not as valuable if we cannot conclude something. So I'm not going to do a whole bunch of stuff just to go, oh, I didn't find anything out. I mean, that's still allowable, but we want to conclude something. So we have significantly different results. What the heck did we just do? Why did this work? Well, we got a z-score. We took our statistic minus a claim. Sometimes they'll put a little knot on that. And then they put P, Q, N. So basically it's what? 0.67 minus 0.58 over the square root of 0.58, 0.42, and we sampled 100 people. 0.67 minus 0.58 divided by the terrifying square root, 0.58, 0.58, 0.42, 1.82349. Our alternative was that it was greater than. That makes this another right tail test, which means I'm going to do norm CDF to the right. So it was 1.82 to infinity 0.1. Norm CDF. Our answer to infinity 0.1 implied 0.034114. That is the same that they got. Basically what we did is we took and we assumed that the 0.58 was the truth. And we found the probability that we would get the result 0.67, and the probability on that to the right, hence a right tail, was 0.034. Where would 0.5 have been, right? 0.5 would have been further to the left. So the case, it would have been a greater probability. So then this result was to the right of that, makes it significant. It's past that. That 0.05, that alpha level, that's why we call it the significance level. Anything past that will have a probability less than that, which is why we call it significant. Anything to the left of that would have a probability greater than and would be not significant. In your work for a real estate company, you find a sample of 722 found the real estate agent through a friend. I'm going to call that success. Use a 0.01 significance level. What is that, right? Well, significance level again is alpha. To test the claim that 44% of homeowners find their real estate agent through a friend. Okay? So how do we test that 44%? We start with PRTC. Proportion of homeowners who find a real estate agent through a friend. What are the requirements? Data must be collected. It says you found in a sample. Did it state that that was done randomly? So this is going to have to be assumed. If I find out later on that this is a biased sample, then the results are not valid. Okay? We're going to put assumed here. How many successes did we have? I don't have to calculate it this time. It told me. 722. That is more than 5. How many failures? Well, 1762 minus 722. How about, what is that, 1040? Also greater than 5. With all that done, we're ready to run the test. 1 prop Z test. Hypotheses. P is equal to, what's the claim? They claimed 44%. What's the alternative? I don't know why I put an equal to there. Alternatively, well, this is what they're claiming, that it is 44%, right? Are we saying, is there anything in there that says, no, we think it's more? We think it's less? Well, if they don't have those words, then we're testing this claim. We're basically saying, is it different than 44%? That means not equal to. Okay? So, we're going to run this test. I think we're pretty much ready to do that. Let's go to the calculator. What are we doing? Tests and a 1 prop Z test. Our claim, 44%. How many successes? Is it 722 out of 1762, and the alternative was not equal to, so we actually don't have to mess with that this time. Z is negative 0.2557. Make sure 2.557. P-value is 0.011 if I round that. What was our alpha level? They told it to us this time, right? So based on this, what's our conclusion? Since the p-value is greater than alpha. Not by much, but it is greater by like 1,000. We fail to reject the null hypothesis. We get to conclude nothing. We have insignificant results. This sucks. Well, what do we do? Well, we don't just go, well, it's close enough, we'll just reject it. What you could do is you could actually increase the sample size. So if I saw this probability and I had a larger sample size, that would change the results. So if you're not happy about this, if this makes you sad, if you want significant results, we can make our results significant by, we could change the alpha, but that basically opens us up to the probability of being wrong. So that's not something we necessarily want to do. Okay, they set it at 0.01, kind of a proof point here, but the idea is, right, if it was 0.05, we would have rejected. We had it at 0.01. Or we can increase the sample size. What does that do, right? Well, a larger group deviates less. So if my results had been, let me write this out. If I had had 7,220 results out of 17,620, what I did is I just multiplied each one by 10. So the proportion is still the same, but we have a lot more sample size, right? You're like, well, that should be the same. Well, you're right, the z-score will be the same. I'm sorry, the z-score won't be the same. The distance away will be the same, but the standard deviation is much smaller. You have smaller deviation, which makes our results more significant. So let's test this out. One prop z test. Same claim. What was it? I lost it. Where is it? 44%? And instead of 722, I'm going to put 722 0. And 1762 0. Same proportion, but look at our p-value. Look at our z-score, negative 8.08. That's crazy. We're like 8 deviations away, right? The p-value is e negative 16, right? That means 6.2 times 10 to the negative 16th. This would have 15 freaking zeros. 3, 6, 9, 12, 13, 14, 15 before we got to that 6. This would be significant. Okay? So don't just fudge the numbers. If your results aren't significant, then increase your sample size and see if that gives you significant results. Okay? Don't fudge the numbers and don't just start playing with things. You can always increase the sample size. If you see the change over a larger group, then basically that is more significant. Okay? Real quick, I do want to discuss how we got these numbers. We know the z-score by now, so I'm going to do that a little quicker. Z is equal to I don't have that, so I'll use the number from here. The p hat is 0.409762. So that's p hat, where is it? 0.409762 minus the claim. The claim was 0.44 divided by the square root of 0.44, 0.56 divided by, and what was the sample size? 1762. I'm not going all crazy with it, just the regular one, okay? So that gave me my negative 2.569. My numbers seem a little more off, so maybe I did round off a little too much. So I'll just use it, 2.569. Maybe I used it wrong up here. 2.5, I don't know. 1862. There just must be some round off error in there somewhere. That's okay. So 2.57 I'll use. Okay? So the problem here is that if I was to find the probability of this negative 2.57, remember I assume that the claim is the truth. We got a z-score of negative 2.57. Where's the probability we calculated? Right? A right tail would be like all of this mess. That doesn't even make sense because our probability was pretty low. So this would not be a right tail. When you get results that are lower, we generally would do a left tail. Okay? So we would do norm CDF. Our minimum would be, I need a little more space there, negative bunch of 9s up to negative 2.57. Now this actually isn't going to be right. Here's why. Norm CDF negative a bunch of 9s to this number. That's not quite the same probability. In fact, it's about half of that probability. See, we were not doing a left tail test. A left tail test is if it had been less than. When the alternative is not equal, this is called a two-tail test. Why do they call it a two-tail test? Well, we just found the probability that we got the results on the left. But we're trying to prove that it was just different, which means it could have been on the left or the right. So for a two-tail test, what we do is we take that probability and we double it. So we take that tail and we basically add another tail on the other side. So I take that probability and I double it, and that's a lot closer to the probability that we had, 0.0101. See how that works? Okay, so our p-value would be 0.0101. This is a two-tail test. We double the p-value. We get two tails. We find whatever tail we have and double it. All right, couple more. Among 734 random internet users, it was found that 360 of them. All right, so what's our P? Proportion of internet users that use it for making travel plans. That was not helpful. Requirements. SRS. Randomly. So it was stated. Successes. 734 is more than 5. No, that was the end. See, I'm getting myself in trouble for speeding up here. 360 of them is more than 5. The rest of them would be the other 374, which is also greater than 5. That's successes, failures. What test are we running? One proportion z-test. Null. P is equal to some claim. What was the claim? 50%. We're trying to prove less than 50%. That's all I need to run this test. Menu, stats, test. The claim was, I think, 54. No, just 0.5. Our number of successes, 360 out of 734. Alternative was less than, negative 0.51, negative 0.52 around that. That p-value is 0.302, 0.303. And an alpha that was not stated, so we use last point. This p-value is big. Since the p-value is greater than alpha, we fail to reject that p equals 0.5. We do not have significant results. That's it. That's what you can expect on the test. That's a majority of the next test. And I know I went through that really fast, but I want you to see that once you know how to do this, these questions don't take that long. Last time, I do want to say why. Just real quick, I mean, I know we know how to get the z-score, so I'm going to just say the z-score is negative 0.52. Okay? How did they get that p-value? Well, the alternative this time was less than, right? So this is not a right tail test. This is not a two tail test. This is called a left tail test. So that would be norm CDF to the left to negative 0.52. Norm CDF, negative infinity, negative 0.52, well, 5167, I'll keep it as exact, 5167, matches that p-value. Left tail test, that's what we do. Visually, what we did, I should have left some space there, but I'll fit it right here. We took the claim as truth. We got a z-score of negative 0.52, and we did the probability to the left of that. So there was a 30% chance that if that claim was true, we would get a result less than that. That could happen by chance. 30% could happen by chance. So our results are not significant. I need the p-value to be less than alpha to reject. Okay? Last but not least, among 785 randomly selected subjects, 18.6% smoke, and the other 81.7% do not smoke. Notice that does not add up to 100%, so there must be people that, I don't know, just didn't vote. But we need to use a 0.01 significance level, so they've specified an alpha. To test the claim, the rate of smoking is less than 27%. So 18.6% looks less than 27%. Let's see if it's significantly far away. P. We are dealing with the true proportion of, looks like people who complete 4 years of college, right? R, what are the requirements? Randomly selected, so it was stated. We have, well, what is our success rate? Well, 18.6% of what? I need that. 0.186 of the 785. We cannot have 146.01 people. Somebody's like, well, yeah, make it 147. Nope, not this time. See, that's if we were doing where we're trying to figure out the sample size. We always round up. This, we actually round accurately. So be careful with that. That's not an A basket issue as far as I'm not going to be freaking out and throwing away points on the test, but this, we would round it to 146, which is greater than 5. How many failures? That's the rest of them. So 785 minus the 146 is the other 639. No, I lost my number. 639. Requirements are met. Run the test. 1 proportion Z test. Menu, statistics, tests, 1 proportion Z test. What was the claim? Oh, we didn't. See, I knew this was going to catch me. We didn't do that yet, right? We have to know the hypotheses. They said 27%. We're trying to say our results are less than 27%. If you don't remember this, as you run the test, that should stop you because they're going to go, what's the claim? You go, oh my goodness, I didn't do the hypotheses. Don't throw away that point, okay? So the claim was 27%. We found 146 successes out of 785. And we're trying to prove that that was significantly less. What do I write down? Z is negative 5.3. P-value should be pretty low. Right, do not write 5.7 e negative 8. You will not get full credit for that. You can either write it as a decimal, or you could write it as 5.7 times 10 to the negative 8, or 0.000000057. Compared to an alpha level of, I think they told me to use 0.01 on this one. I'll double check. Yes, they did. And based on this, we write a conclusion. Since the p-value is less than alpha, we reject the null hypothesis, fill it in, and conclude the alternative. Keep in mind the homework is not going to have you do a bunch of these, but this is what I'm going to expect on the quiz, and this is what I'm going to expect on the test. The homework will separate these little piece-by-piece questions, okay? Some of them will be all put together, but this is what I'm going to expect. So I'm demonstrating what I expect, and we'll have more examples of that before the test.